like, it's like, she telling me I got a pre-lab. Oh, yeah, she's starting. I'm not doing that. Oh, do before. I mean, I already did lab.
Okay, let's get started. So we're going back to interrupts. A few announcements, homework. 4 was given out last week, but officially didn't want to overload you, so it's been released today. It'll be due a week from today. Office hours have moved back to Thursdays. That will be the normal time. And of course, if anybody needs office hours, you can just ask for extra ones. We plan to have the exam graded by Wednesday, hoping in the AM and not the PM, so we can talk about it in class. But that's the goal. From a class point of view, we're here in interrupts, right? You should be finishing lab 3. You're going to start lab 4. Then we're going to have timers and serial buses, but pretty soon we're going to start getting into project time. So next week we'll have a team formation event. That is the correct time and day and location. So that's on Friday. We'll serve pizza. And then before that, you'll have team ideation slides that will be due. Or not team ideation, personal ideation slides, like project slides that you would pitch for an idea to force you guys to start thinking about projects. Then in that team formation event, people who are excited about their ideas can pitch their ideas. Me and Matt will pitch some ideas, and James, and then we'll form groups. You guys can figure out teams. Yeah, any questions about schedule or logistics? Zero questions. Fantastic. Yes?
It has like the wrong dates listed for Thanksgiving break.
It does?
Yeah, so it's like the 23rd and 27th and 25th.
Okay. Great. Okay. It does indeed. Thanks for pointing that out, James. Anything else? All right, that was helpful. All right, so today we're going to talk about interrupt control registers and interrupt flows, priorities. How do we deal when there's multiple interrupts going off at once? But I figured that most of you just brains dumped everything that we talked about last week. Totally fine. I understand how that works. So we'll do a quick refresher to kind of remind you of the most important parts. So we talked about, we talked about interrupts and the basics of polling versus asynchronous interrupts. Types of interrupts, meaning the difference between system exceptions, or we could also say the things that ARM requires there to be versus the external interrupts, external from the core, which are the peripherals that STM will instantiate, whatever the vendor is going to instantiate. We talked about the vector table and stacking, unstacking, so let's talk about that quick. So this is an alternate representation of your microcontroller, different architecture diagram. And basically what we're showing here is that you have peripherals that literally have wires coming from each peripheral that says, hey, something happened, here's my interrupt, and this is the signal. There's a wire going from the peripherals to your NVIC. It's not a bus, it's just a single line, well, for each interrupt, that says, okay, something's happened, now it's the NVIC's job is to figure out what's going on. Yeah, and so if you remember from this diagram, you have like normal code execution, you're moving along, you start in main, then all of a sudden some interrupt occurs. We talked about how the NVIC needs to look up what interrupt that is, and then it stops execution in main after whatever that next function is, or that next instruction is. Or it doesn't interrupt the instruction, it finishes the instruction, then starts doing stuff. And then it does stacking, where it pushes the scratch registers up to the stack, R12, the link register, the program counter, and the program status register, so that it has a complete copy of everything that was occurring in the main processor thread. And the key idea was that the mapping of where the NVIC has these IRQ lines to where in code you're supposed to run your interrupt service routine. So this is code that you're going to write. How does the NVIC decide when some particular line goes up, like some external interrupt? How does it decide which piece of code to write? And this is kind of a mechanical, written in Boolean logic, or not Boolean logic, gate synthesis mechanism that goes and figures all this out. So basically, it's going to go and say, this external interrupt is related to some interrupt number, right? There's a direct mapping to that. And then it calls, it says, okay, the number in that memory location is the memory location where the interrupt handler exists. So basically, it pops that to, or pushes that, or not pushes, it pops, places that in the PC, and that's the next piece of code that's going to be run after stacking. So then you come, you run your interrupt service routine, you do some tasks, and then when you're done, we unstack everything. You got to return the processor back to its normal state, which means you take off the stack R0, R3, R12, the link register, program status register, the PC, put them back, and so that from main's point of view, nothing occurred. It's just kind of like had amnesia for a little while. Some amount of time has passed, but it should be completely transparent to main or whatever program you're running. Of course, you could be in a function. That's where we left off. What questions do you have? Guys are scared to ask questions. It's fantastic. I see one brave person. Yes. And it's just a fancy function call. Is this a function call that you didn't call? It gets called by hardware. And maybe there's a part you'd have to write, which is in the interrupt vector table, you might have to change the location of memory or do something there, but that's your other place where you get some control. Yes. What other questions? I see questions. I see confused looks on people's faces. Yeah.
So in the interrupt vector table, do you change, like, so if you wanted to customize what was run during an interrupt, would you change the address within the interrupt vector table, or would you change the contents of the code within the function it calls?
You can do both. Typically, you're going to change this function here, but you can, or the compiler, let's be more accurate, will choose where that, the linker is going to lay this thing out, all your files, so your .c file or .s files, you're going to lay it out in memory, and it's going to say, okay, this thing happens to be at that memory location, therefore, because it was the interrupt handler for SVS, I don't even know what that is, I have to go put the address there. But I just pointed out that you as a programmer could change these things. You can't change how these interrupt lines get masked to those particular interrupts. That's not changeable by you. Does that answer your question? Okay. So let's go on to new stuff. So there's some open questions from last time. So how do you set up and control interrupts? What happens if more than one interrupt happens at one time, or what happens if some interrupts are more important than other interrupts? You don't want to necessarily, if your device has to reset or is crashing or something, you have a bus fault, you don't want to be doing some GPIO interrupt. That's not the most important thing to keep your system alive. And so how do you control that? And what happens if you're doing some critical code that can't be interrupted? I don't know what that would be. Maybe you're applying the ABS brakes on your vehicle, right? And you have to actually do the pulsing. You don't want the windshield wipers to go and interrupt that. Windshield wipers are important, but not as important as brakes. So how would you ensure that things get executed? So all this is generally part of the nested vector interrupt controller. Just like everything else, it has control registers. So we talked about some of these ideas already. ARM gives you these system exceptions. It gives you the lowest 16 interrupts from the vector table are defined by ARM, and then the manufacturer has the upper peripherals, 0 up to 239. But for our particular device, right, we only have 96. right? Because it was just too costly. There's no big advantage of having STM implement all 240 if it's more than what's required to get the job done. It just adds complexity and power costs and all those other things that come with larger processors. So they only, for whatever reason, this particular microcontroller, they felt they could get away with 96. I'm sure it was a good decision. That's what they did. So there's two ways to control, or two sets of register banks, and it's good to understand conceptually how it works. So you're going to have registers that are used to like enable interrupts, to disable interrupts, to set the priority, and there's two places on your device to do this. So ARM specifies that there is a bunch of CS or CMIS, I forgot what that stands for, but their register cluster, they must have like enable pins in there because that's what the core, or that's what the NVIC uses. But they have duplicate registers oftentimes. The manufacturer's registers are in the, say the peripheral, so a GPIO pin goes high, that's where they're going to control it. So that gives you two different programming interfaces, two, in a sense, of registers which you can control, and usually it's mirrored between them. Just so you know, there's two locations. And so these are the ARM ones. Let's see, it's probably easier to look at it this way. So we have things like a register for setting or enabling interrupts, and then one for clearing enabled interrupts. We have, now these are different functions. For the same register, you get set register, and for the same function, you get register just for setting and then just for clearing. We'll talk about that in a minute. You get to figure out which interrupts are pending. And pending means an interrupt, one of those lines has gone high, but we haven't had time to service it. We haven't had time for the NVIC to go in and pull the interrupt service routine. That could be because it's been disabled, it's just pending. You're not supposed to respond to it, or it could be you're very deep in a very, like maybe you're 20 interrupts deep and you just haven't had time to get to it. So that's why there's a register that just holds which ones are pending. So we can enable it. We have registers for pending. We have registers for identifying which interrupts are actually active at the moment. And then we have registers to control the priority, to explicitly say this interrupt is more important than this other interrupt. So when your bus faults are going to be more important than GPIO because you can't even get GPIO messages back if your bus is failing. Okay. Any questions so far? Yeah.
Both interrupt set, enable register, and interrupt clear, enable register.
We'll talk about it in just a minute. It's a great question. Yeah.
These are like each of these. Wait, so there's one set of these for each interrupt?
Correct.
Okay.
Let's say it another way. There's a register, let's say the interrupt enable register, that has bits that correspond to all the interrupts available. So it's not just one register for one interrupt. It's a bank of registers with one hot encoding for each possible interrupt. We'll show that in a second. Why don't we just go ahead, and then if I didn't answer your questions, we'll get back to it. And here's this. So these are the examples of the, come back. This is like the ARMS interrupts. And this is just a quick example of STM's interrupts. And you see here, they're showing you the address, the name, and then there's the same sort of functionality. You have interrupt set enable registers, clear enable registers. So the same method is just in a different location. And so how these are laid out is that you have a register. So this is set enable register 0, and it's one hot encoding. So we go here from the lowest register number or interrupt number all the way up. So you're going to have multiple 32-bit registers. You have your index, you have an enable bit, it's just saying if it's enabled or not enabled, and then you have the interrupt number that's associated with that. So basically, just like when you're setting up GPIO pins, you got to go figure out, okay, this register represents a GPIO pin, and I have to set if its load is high or low or input or output. I have to go set if the actual output should be 1 or 0. Same concept here, you just have to figure out which one represents your particular interrupt if you're going to enable it or disable it. Yeah, and there's n number of these. So there could be up to 7 for ARM, but for us there's only 3 because we only need 96. There's the quirk of these things where you have set and clear registers for the same data. All right, so basically you have two different addresses for the same amount of data. I have one address where I would go and put a 1 in at some location, and that will set it. And then I have to, if I want to clear it, I can't write a 0 in there. It will not work. I have to go to a different register with a different address and then say I want to clear it, so then I'd put a 1 in that register number to clear it. So why did R make this choice? Why don't you take 30 seconds, talk to each other and say, why would they make it so difficult that there's an address just for enabling and a separate address just for disabling?
Really stumped by this one.
Guys, I thought it was kind of like the priority if something's pending.
Maybe because like you can't just clear it, like the system has to do some stuff to like actually clear the interrupt. So like if I just set the bit to 0, then
All right, why would they make this choice? What do we think?
Because ARM is a business, it might have been significantly cheaper and simpler to implement it this way.
Probably not. I mean, significantly probably doesn't make any difference, but it does require the programmer. So it's the same amount of, it's the same under the hood registers, right? It's just now we have two different addresses to control those registers with specific functions. Yeah.
It's a lot easier to detect if wire goes from 0 to 1 or 1 to 0, but not vice versa. So it's easier to go from 0 to 1. So we have both checking if it goes from 0 to 1. But if you have one that checks for both, it'd be kind of difficult.
I don't think this is about checking, but I think maybe I understand what you're saying. Yeah, one more.
That makes sense because you have to do masking for other things like GPIO, but it does make it easier in the sense that you don't have to mask it, and there are less steps for the user to do to be able to clear and interrupt it.
Right. So there's less computation. You don't have to make a mask and OR it in and then put it in there. So there's less computation. That's absolutely true, and this happens a lot. What's another reason? Considering the interrupts are super important and your system may not work properly.
So to prevent you from accidentally clearing them?
Pretty much. This is just a helpful thing. If you all of a sudden turn all your external interrupts off and then none of your buttons work, and then the user can't power on reset their thing, and now you have a brick. So just another layer of redundancy. So yes, it helps with coding. Just make sure that you don't have to go and load the whole register out, figure out mask and put it back in, but also just a level of safety. Yeah.
If someone accidentally, I don't know how you would accidentally do this, but if someone set the ICDR all to 1s, wouldn't that do the exact same thing?
Yeah, you can mess it up. I'm just saying there's this another layer here of redundancy. Is that maybe the main reason? Probably not. It's probably more just to make it functionally easier to do from a coding point of view. Yeah. You have a question? Nope, just stretching. Fantastic. I guess I should have put this line first, but this is just an example of, what's going to happen here. So you would, logically shift over, say it's the 18th location, put a 1 in there. That will cause a 1 to appear over here. And then if you want to erase something, then you have to put a 0 in this one, which will cause something to be cleared over there. So you can advance animation, so that would become a 0. So it's the same register underneath. It's just two different addresses to look at it. In your, these are the registers for your particular data sheet. When the interrupts trigger the hardware is pending. Oh yeah, so is your job when you're looking at the pending register, so say you've enabled it, you have the pending registers here. In the ISR, it's your job to deassert the pending. So basically your NVIC says, hey, there's an interrupt here, it's pending, and then your NVIC will go through and choose, okay, it's this thing's turn to go and fire, but when you run your interrupt service routine, you have to say, I'm done servicing this interrupt. And so you have to deassert pending. Yes?
Can you read these registers or only set and clear them?
Let's see, these are, you can definitely read them. I was just looking to see if they say read write, but yeah, you can definitely read them. It's not that often that you have to, because the NVIC's taking care of a lot of that, but you might say, look at all the pending, you might want to see before you enable interrupt, it could have a bunch of pending things, and you don't want to just jump into it, so you can see, are there pending interrupts for this particular thing, disable all of them, or sorry, clear all the pending things, then enable the interrupt. Yeah.
They're different, like, are you responsible for handling the reset of the pending bit differently if you want your interrupt to like run continuously as long as the interrupt signal is high? Is that a situation you would run into?
I will go through some of those timing things, but if you want your interrupt deasserted, not to be cleared, then you're responsible for doing it. If you, for some reason, want it to fire immediately again, then you would not have to unappend it. You just exit it, and then you'd have to go right back into it, depending on if it was the next thing in line. We'll talk about that. Okay. Let's see, what else do we have? Interrupt status register indicates which interrupts are active. And that's kind of a weird one because you're like, well, why do I need to keep track of which interrupts are active? I'm doing a task right now. I should be in an interrupt service routine. But what we'll find out is that you can get interrupted in an interrupt. Right? You can have a higher priority interrupt that comes along, and now you're saying, well, I don't want to, it's not about GPOs anymore. I got to go back to the breaks. And sometimes you could imagine it's useful to say, oh, how many interrupts are actually on right now? Should there be a separate task? Now, that's probably well beyond the scope of 373, but there are times when that's actually useful. So the things you need to worry about here are you have interrupts. They have registers that represent those interrupts once you've set them up in your peripherals, and you can disable and enable them. You have registers to determine which ones are pending, and it's your responsibility to clear them, and you can check to see which interrupts are active. Let's see. So what we'll talk, so it is possible to not required, not often, but you could set up a software interrupt, or sorry, you could trigger interrupt in software. There's a particular register for this, or you could just set the register to pending if you wanted to, or hit the bit in the pending register. This is, sometimes it's edge condition where you're in main and you need to set something up, or maybe you have something that happens every single time and you just want to initiate it without having external event occur. The thing we haven't talked about is that you need to be able to set and control the priority of these registers. We'll talk about that later. Okay, so we'll talk about things as interrupts as a function of time. So here we have worksheets. Let's see. So we have this interrupt request. So the interrupt request is coming from the peripheral going into the NVIC. Then we have an interrupt pending status. So that is the NVIC has identified which interrupt to do and has raised a pending flag in the pending register. There you go. And so that, and it took some time. So the x-axis, which is not clearly described here, is time. Then the processor was able now to start executing it, right? So here it came in, there's some latency, it went high, and now we've made a decision, okay, we're gonna go from threaded mode to handler mode, and we're going to now enter into the interrupt, okay? And then software here caused that thing to go down. Yeah. You guys need more? They'll come down this way. If you guys can move those things down. Sure. Here, they'll move them down and he'll move them sideways. All right. So that's one case. Let's see. So you can have the interrupt request, that line from the NVIC that goes high, depends on the hardware type and how it's been configured. Sometimes they will go up and down. Sometimes they require, in hardware, your peripheral may have a register that says, okay, now you have to deassert the interrupt request signal. So in this particular thing, we're just showing hardware cleared the interrupt request. But it was still caught by pending. So the NVIC caught it, put it in the pending register, and now we're in the thread handler. All right. Some other places you could clear it in software. So here, this is an edge condition, but the interrupt could come. It could be placed on the pending status, so pending register. And then before, for whatever reason, you could exit, software could go and clear that pending register. So when would this actually happen? Again, back to the case we talked about where you have not enabled this interrupt. The interrupt service, the interrupt request from going to the NVIC, that line is raised, it's put into pending, but you have not enabled it yet. And so you don't want to enable your interrupts and all of a sudden have a bunch of interrupts you have to service. So you could go in there and clear in software before it's been enabled. So that is one typical use case of this. But just talking through some things that could happen. So in this particular case, interrupt occurred, it went into pending. It went from pending to active. Processor went, changed modes, did handler in here. The interrupt service routine went out to the peripheral and told it via software, okay, clear your pending flag. Just a different condition. And then you go on with the rest of your thing. So here's for your worksheet. So you guys can fill this out, try it out. Yeah. So what happens in this edge condition here? So we have the interrupt stays high the whole time. Pending comes across, it goes high, it goes into active, so pending is deasserted, we're in our handler, and then active status goes high, but that thing is still running. So take a guess, it doesn't have to be right, just try it out, draw it out, work together, and we'll talk about it. The basic question is, you're in an interrupt, you finished your interrupt, right? But it's still high after you leave. What would probably happen?
Processor goes low after the interrupt and active status goes low. But then
Let's try it out, yeah.
goes high.
Try it out.
Causes the
Could be something.
active and processor to go high again. That's my guess. Because there'd still be an active interrupt request.
Edge of the interrupt request is what triggers the pending. So I feel like if this happens, then
Or the interrupt pending signal or status trigger is high. Yeah, then this is.
I have too many.
It'll just be pending until it becomes active. Like, time shouldn't do anything.
What triggers the interrupt pending status? Like that triggers that. We're not having, we don't have another like up.
yeah, I think
That's really what happens.
I think you just keep running the thread mode.
Everybody who sees it is like, that's most gigantic lunchbox I've ever seen.
Yes.
They go together.
So signal, does that just how
It's no longer pending.
right, so as soon as this goes low, it's essentially like allowing this to mirror this.
My scale right here. It's still high. It's just
This active
So ran a
status right now, yeah.
CSC.
the edge that starts the interrupt.
Okay.
In which case, this stays active.
That's pretty nice.
You start the interrupt again. It's like, if it's active, it'll start, it'll just on the clock cycle.
Say is active high.
So maybe this like checks again.
I'm just like,
Clear of the request triggers.
Pending interrupt request is active high, not edge trigger.
Active high. Okay, yeah, that makes sense. Maybe this is right, fall slow.
This is definitely wait. This is wait.
That's what I
Does it stay?
We're gonna get triggered as pending again right here.
That's every single CS class.
Triggers.
it's all for like semiconductors and I would take.
I'm thinking, what would trigger the pending status to go up?
The active signal, hold on.
I know.
Maybe the interrupt active
No,
status.
that's what he was saying, right?
So I don't think it'll check again until it's not active.
All right, what do we think? What do we think is going to happen here?
another request, so pending is gonna go back up, and then the status is gonna be, down for a second, and then until the pending is done, it's gonna go back up, and then the processor is gonna stop while it's pending, and then go high again once it starts again.
Yeah, kind of feels like that. Let's see what happens. Because the interrupt request always stayed high and active. So here pending, so it went from interrupt request was registered, the pending bit on that register went high. The interrupt, when it was its turn to go, we'll talk about when that happens. When it's its turn to go, it was changed from active, which deasserted pending, because it's not pending anymore, it's active. The handler occurs, the handler ends, active ends. Well, now that we have a case, as that edge goes down, it's not pending anymore. It's not active anymore. So then it goes back up and says, oh, well, the line is still high, so now that causes it to be pending. We go back into the active state, and so you get a little glitch in a sense, where we wasted some time. What did we waste here? What could we have wasted? Yeah.
Maybe you jump back into a singular instruction, you have to finish that, and then go back to the interrupt.
You could. What about a process of going in and out of interrupts?
So we pushed all of the registers to the stack.
Yep.
And then we brought them all back.
Yep.
We finished the interrupt, and then we went, we have another interrupt, so we did it again.
Right. So we're wasting some time. We're wasting all that processing time of stacking and unstacking. And we have a way to resolve that later on, yes?
Is an interrupt ever allowed to interrupt that process?
Oh, the action of stacking and unstacking is atomic, meaning it cannot be separated. So you cannot interrupt halfway in the middle of stacking. Well, let's say it slightly more accurately. An interrupt can occur, it just will not be processed. It will wait. The core and the NVIC will wait until the stacking process is done, and then it will take action on the interrupt that's occurred. Yeah.
So what's the reason that time is a lot shorter the second time?
This is shorter?
Yeah.
Well, you can see the accuracy of which this graph has been made. Okay, so we didn't even, this is kind of, I call it Intel, I worked at Intel, so I'll tease them a little bit. You see the marketing graphs, they don't even put axes labels on there. They're just like, we are better than last year, right? I feel like it's kind of like this graph. Okay, it's just saying that it doesn't have to take a long time for this to occur. It could just take a clock cycle for it to occur. But why did it take longer? I don't know. There could have been other multiple pending things happening over here, but there's no good reason why that separation is longer than this separation. Other than now we're faster. Okay. Any other questions about this? All right, let's go to another example. It could be, we talked about the idea that hardware interrupts, that interrupt requests, that line that goes from the peripheral to the NVIC, could be deasserted by hardware. So maybe we're in a situation where hardware is going really, really fast. It's saying interrupt, 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 interrupt. Maybe it's just somebody's pushing the GPIO pin line really, really fast, or some bus line is causing that to go high. And so in this case, interrupts going all the time. You go pending. Oh, maybe I didn't set this one up quite well enough. Let me see. Let's assume that it takes some amount of time that, because we don't have good time scales on here, let's say it takes some amount of time to go from pending to active. Let's just say it takes at least 3 cycles before you get out of pending. What happens with those to the rest of the diagram? So let's assume, can I draw on this? Ooh, computers are hard. Let's assume it does this, okay? Now go through and try and figure out what happens with all the rest of the time.
That would be it doesn't switch into pan for mode until
thoughts on this? I think after the pending ends, it should be active.
active until all requests are finished. Just not sure what an active processor mode's gonna look like.
So where the mode is gonna go to the interrupt handler.
Actually, wait, my question is, any singular request have like
We haven't, in my opinion, I don't think we have any knowledge the interrupt, about there being multiple interrupt requests, because the only information we have to keep track of is single interrupt.
All right, so what do we think happens here?
I might even,
Yeah.
because of the interrupts, how quickly they occur.
Yep.
You do it, but by the time you're done doing it, like the pending status is not gonna go back up because you've already seen all the
Right. So we can look here. In some ways, it's just as whatever normally should have happened, right? Whatever he demonstrated. The trick here is just because it happened 3 times doesn't make this thing happen 3 times. We don't get 3 interrupt requests. It doesn't keep track of it. There's no mechanism. Remember, so the interrupt goes up and it set pending status high. Pending status high, this line just represents a time trace of a register, of a particular bit in a register, and that register went high, and it was high. And so the NVIC said, are you sure you want to be high again? Yes, I'm high. Is that sure you want to be high again? Yes, I'm high. So that register, pending register, doesn't have any extra information about how many times it was called. It just holds the state one time it was called. And then, all right, so it went to pending. It got out of pending because some event occurred, who knows? And then it went into active state. The handler went high, did interrupt service routine, so it stacked, unstacked, interrupt service routine, stacked, and it went on to its normal way. When it went out of acting, it was able to be pending again, but since the interrupt request was not high, it didn't go into pending. Let's do one more. So let's look at this example. Let's see what we have here. So interrupt, so this is kind of a modification of the last one, only we're going to zoom in a little bit in a sense. So interrupt goes high, we're into pending, we're into active, and then when we're in active, but pending's low, interrupt goes high again. Or sorry, the interrupt request goes high again. So what happens to pending and interrupt status in the rest of this diagram when that event occurs? Basically, before all 3 events happen, before you even got into active, here you're in the middle of active. And these events, another pulse or another high edge comes in. Yeah. Sure.
I'm sure if this is.
Do you have extra worksheets?
The active status will go low. Before the pending status would go high again, then it would go low then high. Should we just?
I guess if you're like, it doesn't. It looks very similar.
No.
I'm just not sure.
You can't guarantee. This one is like
Like it might be a long active status.
Active status is high.
I just
It's just the status.
What assumptions are.
because he's higher than the active, you would just set the handler function.
Declaration selling.
Fantastic. I'm doing great. Questions you got?
I don't know if we have a question.
Great.
Yeah, it just takes an amount of time because it's doing something based on the interrupt.
Penny would go back up here.
Okay.
Now we need to do something about it.
Yeah, because I didn't give you any extra time.
Interrupt request is high, status is low.
Then at some point, active status goes low again.
It starts by this going high, then this goes high, then this goes high.
And so it switches to this once.
Can't go high again.
I just made it happen.
So if we look at it here, like the second one, this goes high, this goes low.
In a sense here, but what do you think, what happens to interrupt pending status when the interrupt is pulsed again?
Depends, I think it depends if the active status goes low or not.
I don't think so. That's good. We're learning here, so it's okay. Well, I would say that it goes high again. So pending is just saying I'm high or low, right? The only thing that causes pending to go low is going into active or having software come through and clear it. So those are the two mechanisms for pending to go low. The reason pending goes high is because the interrupt request has come. That's when it goes high. I guess you could write a bit into it to make it go into pending from a software point of view. But the interrupt request makes it go high, going into active makes it go low unless there's a software intervention. So I'm going to say here, interrupt goes high. We can just advance. This is what I got. So we're back into interrupt pending, okay? And then, which this part was not explained or not drawn to you, but you would assume that at some point the interrupt active status would end because your handler is done. Then we come back to that kind of glitch case where one cycle out, then we have to go right back in, we have to unstack and stack. Yeah.
I'm trying to understand this one compared to the very first example we did, slide 32.
Okay.
I'm thinking so this one, the pending status went up, only went high only once the active status went low.
Ooh, that's a good point. Why was that the case? That's went low. What caused it to go? Was it released when it come out of that?
So true.
Go read the textbook. There is a logical inconsistency there. Okay, so in this diagram, which I stole from the textbook, this goes high. Why does it go high? It's independent of this thing going low. Classic, and then we go back over here. This thing was high, stayed high. Oh, you guys got me. Uh-oh. I'm in trouble.
Do we get extra credit now?
Only on the exam when I mess up on the exam. I'm forgiving you guys here. You guys can forgive me. I'll go figure out what the nuance is there and what that rule is.
There's could be two different rules that set it high. Like this second one, it could be the rising edge on the interrupt request. There is no rising edge in the first one. So it's like it's either a rising edge on the interrupt request or a falling edge on the
I will, this is between slide 3. So I think you're probably right. It's probably some nuance of edge.
Yeah. It wasn't hard enough. It's just.
Okay, we'll talk about that Wednesday. But I think aside from the nuance of is it edge triggered or level triggered, do you have any other questions? Yeah. No, don't listen to him. He's pointing things out. The inconsistency here is why did pending only go back high after active went low, right? So it seems like pending was allowed to go high in this condition, okay? However, if we go over to here, right? Pending went up, independent of the status of active. So that makes it think that this is actually is edge triggered. So I have to go look in the R manual and figure out if that's edge triggered or level triggered. I mean, I guess we could guess the answer there, but I will go find out for sure. Okay, that's a good question. You guys got me? What other questions do you have? Okay, So let's talk about interrupt priorities. So, so the NVIC allows you to control the priority, meaning which interrupt should happen before other interrupts. So do you want your UART to always be sending communications back and forth, or do you want, say, an external interrupt to interrupt it? Which one is the most priority, has the highest priority? And I say almost everything except for, as we'll see, the ARM defines that the interrupts that are used to require to make sure the processor works, like those lower 16, those are not necessarily remaskable. So higher importance can interrupt lower importance interrupts. The lower the priority number means the higher importance. So I always have to remember these is golf scoring rules, meaning that the smaller the numbers, the better. Why did they choose this? Why not just have it be the higher the number, the more important it is? Yeah.
So one's easier to access than
Yeah, okay, yeah.
Because the system interrupts are like really important. So they're going based off of that.
That's good. What else?
It's normally like convention that like zeros, like lower numbers are like higher priority, like that on 1 and 2.
Sure. It's also, so that's right, all these ideas are right. We can also think about the fact that there's no absolute highest number because we don't know how many interrupts are in the system. So if there's some interrupts only have some ARM, so some STMs will probably only have like 24 interrupts or something. Well, how does that system compare to something like the STM that you have that has 96? Does that mean some of those interrupts are more important than other ones? So it just becomes like this remapping problem, and so they just go negative. That's another reason. I see hands, questions. Okay. We have the 3 priorities for the system exceptions. The rest are programmable. And we see here that the interrupts are actually here at address E, blah, 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 right? So this is actually in the system part of memory, right? So if we look at our memory table, we said, okay, there's code and data and flash and your peripheral interrupts and your external memory, and I don't forget what else is up there. And then at the very top, there's systems, because this is part of what the function of the chip, so they have put all those registers up there. Okay, so we talked a little bit about this. They're going to give them a priority number, so a priority number of, say, 5. So say interrupt A has 5. If B has 2, then B is higher than 2. So we're just going to use negative. The exception here is reset, non-maskable interrupts, and hard faults. Those are fixed. You cannot change them. All the others are adjustable. Now, the mechanism for changing them is you have a register, it's an 8-bit register, in which you can set the value of what's the priority number of this thing. Smaller numbers are better. And then there's 2 ideas in here. There's the preemption priority and the sub-priority. Preemption priority is, I'm in an interrupt, what interrupts can interrupt this particular interrupt? Ooh, that's a lot of, say that cleaner. So basically you're saying the lowest value here, other interrupts have higher priority and can interrupt you if you're in this interrupt. Sub-priority says, of things that are the same number, so you get a bunch of interrupts that are about the same priority, what's the order in which they should be executed? So say I have 7 interrupts pending that are all the same priority, then you would look at your sub-priority number to say what's the ordering of those. Okay. And why it says not implemented is on your STM32, they have not implemented the bottom 4 bits. By default, this is the allocation. We'll talk about how to change the allocation. But ARM defines that there must be 4 bits, but STM doesn't use the bottom bits. Why? Any reason you think STM wouldn't use the bottom bits and would only use the top bits? Why not just use the bottom bits? It's a weird choice.
And maybe in other chips, the bottom bits are for sub-priorities when you have interrupts.
That's a good reason. It's not, there's no sub priorities, but you're getting to an idea there. This makes sense, yeah?
They're not implementing all the interrupts, all 230, whatever.
They're not. And also, if you're taking code from one device to another device, and say they use 6, we don't want to have the most significant bits So say you just use these 6, and this would be the most significant bit, and then you take that same code and try to use it somewhere else, and they use the top bits. Well, those priorities won't work together, right? So instead, they said, we'll just use the highest bit, and in this new system, it's unused, right? Even though that they're available, because these are lower bits, they will not be, they will not clobber those interrupts. Yeah. Sorry, say that loud.
Between the two again.
Sure. So preemption priority says which interrupts defines the importance of an interrupt. Okay? That's it. Lower the number, more important it is. If I have the lowest interrupt in that is pending, will get executed first. However, there is a class that you could have interrupts of the same preemption priority, but you have multiple of them. So say I have 5 interrupts pending of the same preemption priority. Well, this tells you the order in which they should be done. Yeah.
It's only space to differentiate between 16 interrupts, right? Like how would you handle
Priorities, not 16 interrupts themselves. There's different 16 levels of importance.
Right, so like couldn't there be clashes where different interrupts have the same priority?
Yes. You would look at sub-priority.
Same sub-priority.
Yeah, then you just look at the, I bet it, I have to remember exactly, but it's just going to be the lowest value interrupt in the NVIC table.
So multiple interrupts happen, one has a higher preemption priority
Correct.
than the other. Both of them still get executed?
Yes, but you can only execute one at a time. So it tells you which the order is. So your NVIC is going to look and say, all right, here's all the things that are pending, which has which is the most important, has the lowest number, and it does that one first.
It still feels like these two categories of bits are still essentially just both used to determine the order.
Correct. That's it. You're absolutely right. Yeah.
Does this just determine the ordering before you start executing the next one, or does it also determine which one can interrupt which other?
Good point. This is which one can interrupt which one. Okay? This one is, of the ones that are the equal importance, which one goes next. But if this one, so say this was 4, you have one interrupt that's 4 here and 2 here, and then while there's another one that's 4 and 1, right? You're not going to interrupt what you're doing right now to go after the one that had, we'll look at examples of this, that has a 1 here. This bit will not allow you to interrupt an interrupt. It just says what's next. So now your statement was kind of like, why are you making all this differentiation if it just says the same damn thing? Well, it doesn't. There's a small difference of this number does not allow you to interrupt anything. Only this allows you to, interrupt an interrupt. So this is the number that allows you to interrupt an interrupt. And we'll go through these examples a little bit more in detail. Yeah.
So for each interrupt, there's only one interrupt.
No. So this numbering scheme allows us to define the level of importance of an interrupt. Correct.
And then anything lower than 54 would go back.
Correct, although these are bits, and this is just saying the bit index, not the actual number, so it would be 11100.
That is priority 4.
Yep.
And a 3 comes along.
Correct.
Interrupt that one.
Correct.
Like if the one that you interrupted initially, like another one comes that's higher than that but lower than the one that got interrupted, like.
This is that priority queue. This is that queue. This tells us, basically it says, the NVIC's gonna go through and say, okay, I'm in an interrupt, is this next thing that came in, is it interruptible? Is it a higher priority and should it interrupt what I'm doing right now? Yes or no? And if it's not, it just puts it back in the queue essentially, in the list of pending. And then when that interrupt ends, it goes through the list of pending and says which one is the most important, and then of the class that's most important, which one is next in the sub-priority. And it chooses to do that one next. Did that answer your question? Okay.
So can you only have 4 preemption priority levels?
In this particular instantiation, but I'm so glad you asked, because you may want to have more. I understand that. And for you, they have designed this so that you can change the allocation of these bits. So you could have 4 bits for preemption priority, but have no sub-priority. You could have 3 for preemption priority and 1. You could have whatever combination they allow through these things. So basically, you can allocate the distribution of those registers, or those bits, for how you want to do preemption and sub-priority. I think the programmers found out that having all these, they could have given you STM. ARM gave it to you. STM took it away, those guys. ARM gave you 8 bits. STM only gave you 4, took 4 away. What you're going to find out is having lots and lots and lots of different levels just makes programming hard, because that's so much you have to keep track of. So having a basic scheme, and this is the default scheme, 2 bits here, 2 bits here, is probably going to solve most of your problems. Yeah.
So we have one register that tells us how the bits are allocated.
Yep.
And then does every
that's the word I'm looking for. Not interrupt. Does it where do I actually set and I say this interrupt has this priority, this interrupt has this priority?
This priority distribution is for the entire chip, for all programs. It's not per device.
I'm saying for a given interrupt, how do I give it the priority that I want to give?
We'll get to that in a second. There's a register for that. We'll talk about that. Yep.
The preempt to 0 bits, how does it handle the system interrupts that are always interrupted?
No interrupt will be able to interrupt.
How does it know that they're supposed to interrupt everything?
Got me again, you smart kids, adults, sorry. I don't know how. You're right. So if you set it to 0, that would imply, well, if you set it to 0, that means no interrupt can be interrupted. That might be valuable. It just says, then you just use your sub-priority bits to say what's the next available interrupt. But you're right, it does imply that if you had a system reset, that you could not interrupt. The system reset being the most important interrupt possible, could not interrupt an interrupt. That seems weird to me. I think that might be actually the case, though. I have to look into that. Because you've redefined the priority distribution. Okay. All right, let's go forth. Because setting these priority bits in that distribution is so important, the programmers want to make sure that, or the architects want to make sure that no bad things happen, right? That you don't accidentally redistribute that, because now your device could have drastically different behavior. And so in lab, and just in general, you will, if you have to reset your priority groups, what they require is that you send a special key that's a known key. You have to write this number, hex 5FA, to the vector key to a register. You have to store it in there first, and that allows you to change the priority group distribution. Just they're so paranoid that errant code is going to mess this thing up. Something bad's going to happen, and then you've bricked your device, that they say you have to put a key in there. So one instruction, one store here, and then another stored after to change that distribution. All right. So we asked about how to set this. So there is the priority queue. I forgot what it's actually called. Interrupt priority registers. So basically, they're 8-bit wide. You have a base register, so you can imagine in memory they're just concatenated, or they're just 32 bits wide, of course, but you're just writing byte-wise. And then here you're setting in the interrupt priority for each individual device. So you can go and say this is its preemption priority and a sub-priority for each individual interrupt. The system has its own priority bits. You can remask some of them, but most of them you cannot. So like bus fault interrupt, you can set as priority, fault interrupt or usage fault interrupt, but you can't do things like hard resets, hard faults, and power on resets, if I remember. All right. There's some other registers that are important to realize, maybe not everyday useful, but just generally useful. So the base priority register allows you to set the importance level of things that should happen right now. So for instance, you may be in a critical piece of code. You don't want anything to interrupt you because I don't know what you're doing, calculating pi, or I don't know, maybe figuring out some, the distance between something, right? So the velocity of a wheel in a moving vehicle or something. You have some critical code, you don't want to interrupt this, so you just basically say, I'm going to change my base priority, so only things that are priority below this number can be interrupted. So it's a quick way to ensure that your code's not going to get interrupted. So base priority registers for that. So it's a base priority mask. Used to disable all the things except for the non-maskable interrupts and hard default. And then you could just do the fault mask, which allows you to interrupt everything that's lower than priority 1. So basically, they're just giving you these extra registers that allow you to control what interrupts are active rather than having to go through. You wouldn't want to go through and say, I have 96 interrupts, and I want to go and disable each one individually. You can basically, this is allowing you to disable interrupts by their priority numbers rather than individual interrupts. So it's just giving you a couple different ways to make this faster and easier. Okay. Let's go through some examples, and I think it'll become much more clear. So in this example, here we're in a program, and then we're just going to show hardware actions, things that are happening in hardware above, and things that are happening on the core. In program space, we have our program stack. We have our interrupt priority table. So this is showing of the interrupts 0 through 4. Here is their priority. This is our base priority, meaning that it has to be a value smaller than this in order to cause an interrupt. So everything is smaller than that. We have our list of pending interrupts. So 0 through 4 are the only interrupts that are available or possible in this little system. Nothing's pending. They're all enabled, and nothing's active. How do I feel about the setup here? Okay.
Sorry, I think I got lost. How do we get to the priority table again? Like if I wanted to set the priority level for 4,
yep.
How would you do that?
You're talking here? Where are you talking?
Wait, so like this, so setting these priority bytes would set the priority for each individual interrupt. Or for each individual.
This sets the distribution. So we have these 8 bits, these lower bits don't count. These upper 4 bits, we can say these 2 are allocated for preemption priority, these are allocated for sub or some other distribution. This is
per peripheral or per interrupt?
This is for the entire chip. This is how interrupts that will be stored. This is how interrupt priority numbers that will be stored here should be interpreted.
But then how does interrupt like 4 have a priority number and then interrupt 3 have a priority number in the priority table?
Because you've written in there, you're defining with those 8 bits in a different register. Yes, you're going to write it into here. You're going to set my GPO has this priority. My serial communication has this priority.
And it's these registers that
yes, these registers control it. Cool. This register controls how the system interprets those bits.
Sorry, thank you.
No, that's good. Better get these things understood now. What other questions we have? Yeah.
I don't understand why it's been designed like this. 'Cause to me, having the priority table, it seems like it's a really wrong base of the priority table and the highest one. I think it's like comparing all the values of the priority.
Yeah.
Why wouldn't they design it like
your priority table is just a bunch of, it's just a big register and you set it for 1 if that priority is active. And then now you know you just go through and
one swap that hasn't been executed yet?
I don't think I followed everything there, but let me try, and then you come back and tell me what I misinterpreted. So I think what we found is that the system programmers want the flexibility to change the priority of interrupts. Okay. You talked about the latency of figuring it out. It is all just combinational logic. And so it should happen in 1 clock cycle. It consumes power, so there's a power trade-off of having that flexibility. Does that answer your question?
Yes, but I'm saying that like, because
this priority table to me seems like, in terms of when you're building that logic,
Yeah.
really complicated to me.
Yeah.
Why wouldn't they just make it one long register that says like, oh, this priority has an interrupt that's been activated, process it.
Let's talk offline. I don't think I followed every little piece of that. Okay. Or ask me again in a couple of minutes. Maybe I'll get smarter. Okay. All right, so here's the setup. We have program, we have a stack, we have priority table. It tells us what the interrupts are. You've written into these things to define what the priority should be: active, pending, and enabled. Okay. So let's say, oh, hardware, software, yes, okay. So interrupt request, so one of those lines into the NVIC went high, that corresponds to IRQ4, is gone to pending. The NVIC has started stacking, so put R0 through R3, R12, link register, program status register, and the PC of whatever is running in the program on the stack. It's stacked. Then the core changes its mode. It starts executing the ISR. That's the program that you've written for number 4. So now it's changed from pending to active, and now it's changed its base priority, because now the system needs to know what's the priority of the thing that's going on right now, so that it knows if a new interrupt comes, should it be interrupted or not. So this tells you the current priority right at this moment. Okay. Then you BXLR, which is, remember, that's the link register that has a special value that points to a place up in system memory, or the system part of memory. This basically says, do the unstacking action now, not actually go and execute what's in the link registry. So then we unstack, you've deactivated, and you're back to your normal program. It's a normal case. How do we feel about that? Yeah.
So the base priority comes from the program, right?
You can set it.
I'm saying, like, the IRQ has a priority, and the base priority is just a check saying, okay, this program allows for this level of priority or above. And if the IRQ fits that condition, it executes, and if it doesn't, it'll immediately go back to the program.
It just goes back to pending.
Without executing anything.
We're going to watch in a moment when an interrupt interrupts an interrupt, and if that interrupt has a higher base priority than the base priority, then it will just stay in pending. It will wait until we have an opportunity to get to it. All right. I think I said all this. Okay, let's look at the next condition here. So this is just basically where we were last time. We're in a program, interrupt 4 happened, and we stacked. Now we're in the middle of executing IRQ4. And how do we know that? Everything's enabled. We're in active mode. The base priority of 4 here is what's active, and now we're going to get an interrupt from 3. So I think it's here. Okay. So IRQ3 goes to pending, so that's 3. We haven't started it yet. I mean, we haven't started running the IRQ yet, so we're not in active on 3, but we've stacked. What have we stacked? We stacked IRQ4. So we were in the middle of this IRQ, interrupted, so you still have to go and stack, because when you return to this, you still have to execute exactly where you were in IRQ4. Okay, so we've stacked to stacked, or we've stacked an interrupt. Then we're going to go and run IRQ3. So here, pending's been deasserted. It's active. Now, look, we have multiple active things here occurring. Okay. But our base priority has changed because we're in 3. So now the only things that can interrupt 3 would be, well, nothing on this table. Nothing has higher priority in this toy example, or more important priority than 3. So this is definitely going to exit. We're going to return from this interrupt. You're going to unstack, right? And that unstacking process is no different than when we unstacked in the last example. The NVIC doesn't know, the core doesn't know, it just unstacks. And that just happens to put it back into IRQ4. We complete IRQ4, we're gonna branch again. We're gonna branch that special location in memory that indicates that we should be unstacking. And we unstack, and that puts us back into our program. There should be a little block here that says program.
So the auto unstacking is handled by hardware?
Yeah, you don't have to stack anything. The NVIC does it for you. Yeah.
So are we assuming in this that the priority distribution is like 2 bits for the preemptive and 2 for the sub-priority? Or like, don't we need to know that to know which?
Yes, you would have to know that. We didn't even talk about sub-priority. We're just talking about preemption priority here, but that's true. We would have to think about all those details in a real case.
Because like if no bits were allocated to the preemptive priority and it was only sub-priority, then like we wouldn't have to worry about the order.
Right, then you could never interrupt an interrupt.
Okay.
But we're only really looking at preemption priority, not sub-priority here.
Just an interrupt of priority like 3, and then an interrupt signal for something that's priority 4 goes high.
Yep.
And it goes low before you finish 3. You just never process that interrupt.
So would it go on the pending stack? So if it's on the pending stack, then it will get processed unless something causes it to go off the pending stack. The only thing that can get it off the pending stack is if it goes active or software comes through and it erases it from the pending stack.
Like responds to the signal. Would there ever be a situation where you want it to go low if the interrupt signal goes low?
Probably not, because I mean, there are a lot of ways to design things, but the whole point of priorities is you don't want to have to be, or of interrupts, is that you don't want to have to be so responsive that you catch things. So it's really nice if you just have something happens and then when you're ready, you can come and take care of it, rather than constantly have to be immediately ready at that moment. All right, so this is nested. We have another condition called tail chaining, and this is when something of the same or lower interrupt priority occurs, and then how do we handle this? So this was an example of nested interrupts, which is kind of like the normal case of interrupts, how we think about them. But this is tail chaining of how do you deal with that without having to do the special case of stacking and unstacking. We talked about that little glitch before. So tail chaining here, back to our condition, we're in IRQ4, we are stacked, the base priority has been set to IRQ4, nothing else is pending. So let's say interrupt 1 occurred, and let's say it happened here in the middle of IRQ4. Well, interrupt 1 is priority 10. So it does not have, that is larger than the base priority. Therefore, it's not going to interrupt this interrupt. So you don't interrupt, you don't unstack, because if you unstacked all the way, we could unstack from here, and then you would have to restack, but that would be wasteful. So what we're going to do, instead of unstack, we're just going to wait, and we're going to go to the next interrupt. Right? We're going to look at what's pending. So IRQ1 was pending. Okay? And we know there's something pending, so there's no reason to unstack. That would just be wasteful. So we're going to go to, now we're going to do IRQ1. Okay. Now we do pending. Oh, and then the base priority when you left IRQ4, the base priority went up, in this case, up to 256. It could be smaller. It could be whatever you've set it to. Then it goes to IRQ1. Then after that one executes, we unstack all the way because there's nothing else pending, and we go back to the program. Sorry. Raise no questions. All right, one question. Thank goodness.
So that little gap
that's in between those two ISRs, is that like it beginning to stack, hesitating, and then keep going because it saw something was pending, or is that just like
that's the time it takes to go find the next instruction, it's time for the NVIC that goes through, processes all the pending things, so it does take some cycles to do.
Okay, but significantly less.
Yes. Yep.
Wait, why is it tail chaining again? Because
Why is it what?
why is it tail chaining?
Tail chaining. Tail chaining is just the idea that instead of interrupting, you're interrupting interrupts, which would be nested interrupts. Tail chaining is the idea that an interrupt occurred, level 1 interrupt occurred, which was less important, okay? Therefore, it should not be interrupted. Therefore, we're gonna wait until we're done with this, but we don't wanna go unstack all the way and restack. So we're just gonna go and add it back on. So it's just, it's a chain of interrupts, and you're gonna add this one to the tail of the chain.
I'm just doing the interrupt later.
Yep.
What's the difference between level 4 and IRQ, like 1? Why is it level and then IRQ?
So what's the difference? What's the difference between level 4? I don't know. IRQ level. I don't know. Are you saying that slide change is something weird? Yes, I inherited these slides. It is weird.
Okay. Yeah, I just didn't know if like ISR level 4 meant something different than ISR IRQ 1.
No, I'll take a note for that. Thank you. All right, let's get to the last condition here. We talk about late arrivals. What happens essentially if an interrupt occurs while you're stacking? Okay, so let's talk about that here. So in this case, we're in a program, interrupt 4 has caused us to stack, but while we're in the process of stacking, interrupt 3 occurs. So what should the system do? Right, because it already started trying to do number 4 here, but 3 is of a higher importance, a lower priority number. So the idea here is, do you stack again? Well, there's nothing to stack. That doesn't make sense. So here you're just going to switch which interrupt vector essentially, or when you go to NVIC table and you look up the IRQ, you're just going to switch which IRQ gets done. So first you're going to do IRQ 3. So even though IRQ 4 is what caused us to stack, just before you end stacking, the hardware goes and looks and says, of the things that are pending, come here. So in this case, it has 2 things pending at this point at the end of the stacking, and then it just double checks. Before it starts executing the interrupt, it just checks which one is the most important. Even though IRQ4 called the stack, IRQ3 gets to be run. So you don't do that, you don't stack. Basically, you just go through, you do tail chaining here. Even though it's a late arrival, you do the late arrival, you do tail chaining. The next thing that occurs here is IRQ4, which is less important than IRQ3, and then you unstack from there and go back to the program. Other questions you have? Yeah.
There's obviously unfortunate cases, right, where you do the stack and then you
Start, let's say ISRI.
let's do start 4.
Yep.
Like you barely started.
Sure.
And you get interrupted.
You'd have to put stuff on the stack at that point, wouldn't you? And it's just like unfortunate that you did almost nothing.
Yeah, we can't solve all cases, right? So this is the case where you've interrupt, and say interrupt that little line here, right, happened right here. You've gone 1 instruction deep. Too bad, you gotta do all the stacking, right? You pay the penalty. It's just, you don't have to pay the penalty if you haven't started anything. Right, yeah?
Interrupts don't assume that there are input arguments in registers, right?
No.
So if you had used it, would you still have interrupt that
well, you don't know what the state of anything on the stack is, right? When you run an interrupt occurs, the NVIC just says, okay, I assume there was important information on the stack. or in the core and saves all those values, right? It stacks them. And then when another interrupt occurs, I guess you're saying you may have not had anything valuable there, but you could have had something. That first instruction could have used R0 for something, right?
So the NVIC doesn't know what the function's using or what it's not.
Right, it has no idea. It's just a hardware process that just pushes things up and pulls it down to ensure that everything seems transparent. Even though you've lost some time, everything should just run. Okay.